In this video, we're going to discuss in greater detail the magnitude of a vector. Again, the magnitude of a vector is essentially the length of a vector. And we've got a couple of ways of describing with our notation the magnitude of a vector. And I apologize for the different ways, but different textbooks, different authors, different mathematicians are going to indicate the magnitude of a vector differently. A lot of people will use two bars, a double bar here, to represent a magnitude. However, when we get into big, complicated problems, having that with lots of magnitudes of lots of vectors, this starts to look cluttered. This notation can look cluttered. There's so many vertical bars at play. So what I usually use, and some other mathematicians use, and some textbooks use, is just a single bar. Now, when what we have inside single bars is a vector, these bars are considered magnitude bars. But if what I had inside these bars, these vertical bars, was a scalar quantity or a real number, then these bars would be considered absolute value bars. So whatever is inside the vertical bars is going to determine or dictate what those bars represent. So in this case, they are mag bars, or magnitude bars. So we're going to discuss a few of the properties of the magnitude of a vector. The magnitude of the vector, being the length of the vector, is always going to be a positive quantity. When we talk about the magnitude of a vector, we get a scalar quantity that represents the length of that vector. The length would just be 2 or 4 or something like that. So when we have a zero vector inside here, we're going to say or answer the magnitude of the zero vector is 0, but this 0 is a scalar, a real number representing the length of the zero vector, basically is 0. Now, to kind of drive that point home here a little bit more, we can say the magnitude of a vector is going to be the 0 scalar if and only if we had the 0 vector to begin with, right? So if this vector is the 0 vector, that's the only way I'm going to have a 0 as the magnitude of the vector. Now, we have talked about the fact that if I have vector v that looks like this, then the opposite of v, or negative v, actually I need to kind of fix that image a little bit. Negative v is going to be just the exact opposite direction, but having the same magnitude. So what we see here is that the magnitude of negative v is the same as the magnitude of positive v. It just means that those two vectors have the same length. Now, this last property is a little bit annoying with its notation here. We have that the magnitude of a scalar multiple of vector v is going to have the value that is now, these vertical bars here, because there's a scalar quantity inside, are abs val bars. So the magnitude of the scalar multiple is going to be the absolute value of the scalar quantity times the magnitude of the vector quantity. So these vertical bars are mag bars. And again, they look exactly the same, but we know that they're absolute value bars on the left because what's inside is a scalar or a real number. We know that they're magnitude bars on the right because what's inside is a vector. So let's just look at a quick example of this. If we were to look at the magnitude of the scalar quantity that is -2 multiplied by v. So what's inside here is a vector, right? It's -2v. If we had a vector v that looked like this, then -2v would be twice as long and in the opposite direction. So what's inside these vertical bars is a vector. So even if we wanted to use that other notation, we could do double mag bars. So for this particular example, let's use the double mag bars. So the length of this vector, or the magnitude of this vector, is going to be the absolute value of the 2 times the magnitude of the original vector v, right? So however long this original vector was, the magnitude of negative 2v is going to be twice as long as the magnitude of the original vector. Again, we're just talking about the length of the vector, and the length is going to give us the scalar quantity that is how long that vector is. The direction is not at play here because the magnitude is specifically referring to the length. And the length of this vector is going to be twice as long as the original vector v, right? Again, we can use the double mag bars if it gets to be confusing with who is an absolute value bar, who is a magnitude bar. But a lot of times you'll see textbooks that are using single mag bars right next door to absolute value bars. And you need to be able to determine which one are mag bars and which one are abs val bars. And the last thing that we'll talk about in this video here is what it means to be a unit vector. Now remember that the word unit in mathematics is almost always going to be referring to the number 1. We've got the unit circle that's a circle centered at the origin with a radius of 1. We've got a unit rate that is going to be like, let's say, a unit rate would be something like the distance traveled per 1 hour, or like miles per 1 hour, or feet per 1 second. This would be a unit rate. So again, we're seeing here that the unit vector is going to be a vector who has a magnitude of 1. And we will illustrate that by saying either single mag bar or double mag bar, that the magnitude of u is going to be 1. And when that's the case, we say that this is a unit vector no matter what the direction. It could be this direction, it could be I could have a unit vector that's going straight down. And just as a reminder that we can either see vectors represented with arrows over the top or with boldface lettering.